Hi guys. Wondering who's this guy? That too. At the start of the video, I won't take a lot of time. Just one request to you all. Watch the entire video. It seems you guys are only watching few minutes of the video and closing it. You don't believe me? Watch this. See, the data clearly shows you guys are watching the videos only for few minutes and closing it. So, watch the entire video and stay benefited. Without further ado, let's start.
Hi everyone, we'll continue with magnetic effects. This is going to be the second part of magnetic effects now. Let's start.
Electromagnetism can be a complicated subject, but luckily you can find two of the most useful tools for understanding it right at the end of your arms. Your hands. They help you to write letters, type on a computer, and throw a frisbee. They also help you understand two concepts of electromagnetism. We will use this battery and wire to create a current so that we can illustrate these concepts. While electrons actually run from negative to positive, the convention is to think of electricity going from positive to negative, so that's how we show it here. When current flows through a wire, it generates a small magnetic field around the wire, as shown by these blue lines. If you hold your right hand like so, with your thumb pointing in the direction of the electric current, then the curl of your fingers will show the direction of the magnetic field. This is known as the right hand rule. We need to reverse the direction of the current to illustrate the other concept. We also need a magnetic field to explain what's happening. These two magnets provide that field, depicted here by the blue lines. When charged particles enter a magnetic field, the field exerts a force on them. You can use your hands to find out the direction of that force. Position your left hand like so, with your index finger pointing in the direction of the magnetic field, your middle finger pointing in the direction of the current, and your thumb pointing up, forming a right angle with your index finger. Your thumb shows the direction of the force, called the Lorentz Force, exerted on the charged particles. This is known as the left hand rule. The right and left hand rules are two handy ways of better understanding the interplay between electric currents and magnetic fields.
Okay, now let's imagine a magnetic field. Let's take a magnet. This is a magnet now, so magnetic field always go from north to south. So let's in this magnetic field, imagine a charged particle enters with velocity v. I'm talking about a charged particle. This can be a proton, electron, alpha particle, but I'm talking about one charged particle. So understand one thing now, I'm very particular about a single charged particle entering a magnetic field, and it should be a charged particle. But what happens is when they enter the magnetic field, what is happening is they will not travel in a straight path and continue moving in the straight line. As they enter the magnetic field, they get deflected towards some side, or they experience a force when they enter a magnetic field. That means whenever a charge enters a magnetic field, they experience a force. And that force is given by magnetic Lorentz force. So understand one thing now. Magnetic Lorentz force is a force experienced by a charged particle, only one charged particle, when they enter a magnetic field with velocity v. Now this is velocity v, and this is your magnetic field b. The angle between magnetic field and this is theta. So they are entering at an angle theta, and this is what happens. So they experience the force now. According to Lorentz, now there's a force experienced by the charged particle, and according to him, now the force experienced F is always going to be equal to QVB sine theta. That means the force acting on the charged particle depends on the charge first. That means if a charge value is more, they'll have more force. So imagine a proton and alpha particle. Proton has got, for proton, the charge is E. For alpha particle, the charge is 2E. So if an alpha particle enters a magnetic field, it will experience more force compared to a proton. So charge matters, number one. Velocity, faster they enter, or they enter with a velocity. And also, if they are at rest, that means when velocity is zero, then force will be zero. So charged particle just being placed in magnetic field will not experience any force. It should move. Moving charge only can experience a force in magnetic field. It depends on the magnetic field B and depends on theta. Theta is the angle between V and B. So when theta is zero, force is zero. So when a charged particle enters magnetic field parallel, or even theta 180, which is anti-parallel in this way or this way, when charged particle moves parallel to magnetic field or anti-parallel, they will not experience any force in magnetic field. So magnetic field will not give any force on a charged particle when they go parallel or anti-parallel. But when they go at 90, they will have maximum force acting on the charged particle. So this is the first thing now. So Lorentz came out with the concept that whenever a charged particle enters, they have a force, and this is called magnetic Lorentz force. And there's something called Lorentz force as well. So when they use the word Lorentz force in your paper or exam, then it's because of both electrical field and magnetic field. Only when magnetic Lorentz force is said, you use a formula now. When they say Lorentz force, it's going to be QE, which is the force due to your electrical field, plus QVB sine theta, which is your force due to magnetic field. So when they say Lorentz force, use both the values. When they say magnetic Lorentz force, use this formula. That's the first information. And the vector form of this is going to be F equals to Q into P cross B. So this is the vector form of your magnetic Lorentz force. You know cross product? V cross B. So V cross B, if you do, the resultant or the final answer, this thing should be in the direction normal to B and B. That means your A cross B, the direction is always going to be normal to A and B. Same thing, this F is going to act at an angle 90 degrees to F and B as well. So whenever a charge, there is a force acting on a body. If this is your force, this is your velocity, and this is your B, and the force will act at 90 degrees to this. So the force will be acting at 90 to B also and B also. So the vectors F and V, that is vectors FV and FB, these two are always going to be perpendicular to each other. So force should act 90 degrees for both magnetic field and the velocity of the charged particle. So the two pairs of vectors which are always perpendicular here are FV and FB, and F should act at an angle 90 degrees to the given field. This is the first information. So this is your Lorentz force, magnetic Lorentz force, force acting on a charged particle. Now, if there is a force acting on a charged particle, then what should be the direction of the force? So it's always 90 degrees to both V and B. It's already known to us. So this is given by your Fleming left hand rule. So keep your left hand and keep your fingers of left thumb, index finger and middle finger in this way, perpendicular to each other. Then these three gives force, magnetic field and current. So here F is your force, thumb is your force, and this is your magnetic field, and middle finger is your current or motion of a positive charge. So force, magnetic field and current. To remember this easily, we remember father, mother and child. Father is force, mother is magnetic field, and child is current. So clearly father, mother, child, if you remember, it's much easier now. So force is your father, magnetic field and current is this. I'll give an example. For example, let's imagine north, south, east, west. Imagine a charged particle moving in east to west direction, let's say a proton. And magnetic field is acting inside paper, going inside inwards. What will be the direction of force? Okay, they ask you. I know proton movement, which is your current, and I know the magnetic field direction. So this is my force. I don't know what is that. So this is my magnetic field, and this is my current. So magnetic field is going inside paper. So I'll first start with the magnetic field now. It's going inside. I'll keep my finger like that. And this is my current. Current is going to go from east to west. So turn. So this says magnetic field is going inside paper. Current is going from proton is going from east to west. So the force is acting towards south. So the answer is towards south. That's your force. So this is the way you use your Fleming left-hand rule. So left-hand rule, you keep your fingers in such a way that it's going to be like that. Or you can use, if you are confused about this, you can use your right hand as well. Right hand this is your force. This is your current. This part is current, and this palm shows the direction of magnetic field. For example, there's a magnetic field acting inside. And a proton is moving in this direction. Then keep your finger like this. This is my proton current. Magnetic field is acting inside paper. So my force will be towards this way. So it will be turning in this direction. So this is the way you can do it now. So this is your current. The palm shows the direction of magnetic field under, and this is going to be your force this way. So you can use this or this. But remember now, if this is an electron, now, then always remember electron the current direction should be reversed. That means when electron goes this way, the current goes in this direction. So current is down, magnetic field is inside, so electron will move that way. So if electron goes in this direction, it goes this way. Proton will go in this direction. So proton, electron always take a different path. If you want to use left hand rule once again, I'll use it now. This is your magnetic field going inside. This is my proton. This is my current, force. Once again, this is my magnetic field. So since electron is going this way, my current is going to go this way. So current is down. So force is this way. So this is, I'll use this as proton movement. But when electron goes in this direction, when electron moves in this direction, that means my current should be downwards. So electron is there, always take the current in the opposite direction. Then it's going to be the easiest way to do. So this is the basic concept, number one. Number two, imagine there is a electrostatic field acting. So imagine there's an electrical field acting in this direction from north to south. And there is a electron entering from east to west. Now, what will happen when electron enters from east to west? Electron being negative, this is a positive plate. Electron is going from, this is west and this is east. I'm sorry. So electron is going to go, is negative, so minus charge. So this is plus. So electron will just go up towards the positive plate. So you can see the electron curving towards the positive plate. So there will be a force acting on the electron, which is F equals to QE, because it's electrical field. The question now is, in which direction you produce a magnetic field so that this electron should go undeflected. So I want electron to go straight. But I know one thing, there is a force acting upwards which is pushing the electron upwards because of electrical field. Now I have to give a magnetic field. But what I should do is, magnetic field force should act exactly opposite to this. That means if magnetic field force BQE, theta is 90, sine 90 is 1. So when this BQE acts in the opposite direction and if these two are equal, then automatically the charged particle will go straight. So when the force of electrical field and force of magnetic field are equal opposite, the charged particle will go undeflected. Now the force is going to act downward. So my force is down. I know this force is down. And electron is going from west to east. That means current goes from east to west. So current is from east to west. So east to west, this is my current. So east to west, force is downwards. So magnetic field is acting inside paper. If I want to use right hand now, this is my force. And I'll come this way. This is my force downwards. Electron is going this direction, so current should be in this direction. And magnetic field is going inside paper. So clearly, the magnetic field should be going in. What you get here is whenever the direction of electrical field and magnetic field are perpendicular, or when electrical field and magnetic field act perpendicular to each other. And if the force of electrical field magnetic field is equal, the charged particle can go undeflected. And this concept is used in a machine called velocity selector. It's called velocity selector. So this is what is used. So when VQV equals to QE, that means the particle will have equal force on both sides. So the velocity of the charged particle can be found out if you know the electrical field magnetic field value. So electrical field and magnetic field value, if you know, simple logic. Make the electrical field magnetic field act at 90 and make a charged particle go undeflected. And calculate the electrical field magnetic field value and divide them. That will give you the speed of the charged particle in a given system. So this is what is your velocity selector all about. And now the formula for force acting on a charged particle is VQV sine theta. Now, what is the concept of, okay, one charge is moving, understood. Now, if there are more than one charge moving in a straight, in a system, going in a one line, all the charges will be now pulled with a force. So instead of telling as a single charge moving, imagine you have a current carrying conductor placed in magnetic field. Current carrying conductor means, when I say current is flowing, means electrons are moving. So you have a wire with current is flowing in that. So you can see electrons moving in the wire in one direction. And these electrons which are moving in the wire is placed inside a magnet. So magnetic field is there and charged particle is moving. So all the charged particle will experience the force of what we had just now. One electron will have force of VQV sine theta. Like that, every electron in the wire will have a force. So the complete wire will experience a force when you place in magnetic field. So a current carrying wire is placed between two magnets and you must pass current through it. You can see the whole wire moves because every electron moving in the wire experiences a magnetic Lorentz force, and that's the reason why they are totally moving. And we have to find out what will be that force experienced all about. So our next topic we're going to do is what will be the force experienced by a charged particle by charged particles, we can say, or we can say a current carrying wire placed in uniform magnetic field. So let's do a derivation. So what I'm trying to find is force experienced by, so right now, force experienced by a current carrying wire placed in uniform magnetic field. So I've got a current carrying wire already there. It's already having current in that, so electrons are moving, and it's placed in magnetic field. So when you use Fleming left-hand rule, you'll have force experienced in the charged particle. We have to find the force. Now, we know force experienced by one electron. According to the magnetic Lorentz force, force on one electron is QBB, Q into B cross B. Let's take it that way, Q into B cross B. I can now rewrite this Q into B cross B as, because charge of electron is always going to be E, because we know Q is equal to NE. When N is equal to 1, Q will be equal to E. So I can write Q as E. So I can write this as E. And velocity of electrons in a conductor is always going to be average velocity. It's called drift velocity. It becomes Vd cross V. So this is going to be the force acting on one electron. Now what I should do, find the number of electrons in the wire. Let the wire has length L, area of cross section A. So let's consider, to find out the number of electrons in the wire, small n to be number of electrons per unit volume. N per unit volume. So this is going to be equal to N upon AL. So number of electrons will be NAL. This is the number of electrons now, and this is the force on one electron. So complete force on all the electrons total will be, you multiply these two. That means E into Vd cross B into NAL, which is E we can write NALE, VD cross B, you can write as VDB sine theta. So I get F equals to this. Now I know what is NAEVD. NAEVD is called current I. So let's use the formula of NAEVD equals to current. So we studied in current chapter. So since I equals to NAEVD, so I get F equals to ILB sine theta. This is going to be my ILB sine theta. So the force acting on a conductor placed current carrying conductor placed in magnetic field is always given by I into L cross B. So this is the force acting on a conductor placed in uniform magnetic field. So we know force acting on a charge. We know force acting on a wire. Now, if I have a rectangular coil with current, imagine I've got a north-south. I'll place a rectangular coil and pass current through it. Now, what will happen to this coil when you pass current and place a magnetic field? So the north-south, the magnetic field is going to be in this direction, north to south. So let's see what happens to this and this. So here, magnetic field is going in this direction, and this wire is parallel to it. So they are parallel. Here, force acting formula is going to be ILB sine theta. So sine theta, when it's 0, it's 0. So there's no force acting on this part. Let's name it as ABCD. Let's name it now. So BC will be 0. Similarly, AD will also be 0 because it's 180 with magnetic field. AB, it's 90, and your CD will also be 90. So I get maximum force in these two conditions. Now, so no force on top and below, okay, and there's no force. There's a force acting on these two. So what's the direction of force then? Magnetic field is this. So this is magnetic field for me. Current goes in this direction. So my force will act outwards. That means this wire will be pulled out. There will be a force acting outwards this way. What about this line? Magnetic field is this. Current is going in this direction. So force will act downwards. That means the force will pull the coil inwards. So clearly, this rectangular rod will rotate because one will pull it this way, one will pull that way. So they will rotate. And if these two forces are equal, they will only rotate. Because when F1 and F2 are not equal, then there will be a chance that F1 is more, they move this way or that way. Here, F1 and F2 are equal, they form a couple, and the whole thing will start rotating. So what we are finding out is, whenever a rectangular coil is placed in magnetic field and current is passed through it, then there will be rotation. When there is rotation, that means there will be torque experienced. So the derivation we're going to do now is, what will be the torque experienced by a rectangular current carrying coil placed in magnetic field. So the idea is to find torque in a rectangular current carrying coil. And I'm saying only torque is there. That means net force is 0. You have to prove that as well. And we have to prove this thing. So let's do some small changes here. I took the wire parallel. Let's not take it parallel. Let's make an angle to this. So let's see to it that you have force on all four parts of the wire. Let's name it as PQRS because B is already magnetic field there. Two B's coming into the picture is not going to be good. So let's take PQRS as a wire. Let I be the current flowing in this wire. From north to south, magnetic field is going to be there. So magnetic field lines are going to be this one magnetic field line for this one magnetic field line for this, and this is a magnetic field line. I'm just drawing 4 magnetic field lines to show the angle. Now, this is my theta. Theta is the angle between the coil and your magnetic field. But the theta I wanted is between the current and the magnetic field. So current is this direction. Magnetic field is this. So this is my theta. The theta here is going to be 180 minus theta. Here, this is my current. This is my magnetic field. So theta is 90. This is my current, this is my magnetic field, theta is 90. And this is my magnetic field, this is my current, theta is theta. So the forces are, angles are theta, 1 minus theta, 90, 90 theta. These are the four angles you're taking. And there are four forces acting now because it's not zero here. So there'll be a force acting on both. So one force will act upwards, which is, let's take it as F1. One force will act downwards, let's take it as F2. One will act outwards, we've already seen that. And one will act inwards, that also we have seen. Now I have to prove there's a torque. That means I have to prove F1 equal to F2 and F3 equal to F4. But I know very clearly that F1, F2, F3, F4 is not a formula, because when I'm current carrying wireless base, we already know the formula now. The formula is F equals to I into L cross B. So it's very simple to do it. So what you do, let's start with F1. F1 will be I into L. The length is this part. This is your breadth of the conductor. It's a rectangular coil. This is length. This is SP. So I'll take this SP as a vector cross B, which will be I into SP is a breadth now, so B cross B, which will be IBB sine 180 minus theta, because the angle here is 180 minus theta for me here, which will be IBB sine theta. So this is my F1. Let's go for F2. F2 will be this way, QR. So I into QR cross B. QR is once again the breadth of the conductor, B cross B. Here theta is theta only, so IBB sine theta. So clearly your F1 and F2 are equal. So they are equal opposites, so they cancel out. Now F3 and F4 are the next part we will do for. So F3 will be equal to, now F3 acts on PQ and F4 acts on RS. So I into PQ cross B, which is I into PQ is the length L, so L cross B. Here theta is 90 on both the cases, so ILB sine 90, which will be ILB. Similarly, F4 will be equal to I into RS cross B, which is going to be I into L cross B once again. So I into LB sine 90, because theta is 90 once again there, it's ILB. So clearly F3 and F4 are equal. This F3 and F4 are pulling the coil in this direction and making them rotate, so they form a couple. So what I'll do, I'll draw this PS part once again, and let's make a diagram. So PS, let's enlarge it and make it once again. So PS part, let's draw it once again. This is S, this is P, this is your magnetic field, you can see, this is theta, this is your F3, and this is your F4. Now clearly this is rotating. So my torque formula is always going to be equal to, you take any force, either force, into your perpendicular distance. So my F4 into my perpendicular distance, let's take OS, or F3 into OS, anything is okay. So my torque will be F4 into OS. Now this is theta, this will be theta, you know math. This is B, the breadth of the conductor. For this triangle OSP, triangle OSOP, you can say OSP, cos theta will be OS by SP, or OS by small b. So OS will be equal to B cos theta. So this is going to be ILB is your F4, and this is your B cos theta. So clearly length into breadth is called area. So torque for a coil rotating in magnetic field is BIA cos theta. This is for one turn. If there are n turns now, the formula will be torque equals NBIA cos theta. Here theta is the angle between the coil and magnetic field, and this is theta field. Normally torque is a vector quantity, it's always in terms of sine, but take a normal. And let this angle be alpha. So theta can be returned as NBIA cos theta is 90 minus alpha. So this is going to be NBIA sine alpha. So this is going to be my torque in the coil. To remember this formula now, you can always remember torque will be equal to Vina sine alpha. Vina is, you can remember this word, Vina. The information is normally when you have a magnet, north and south, there will be a magnetic moment acting from south to north. And that magnetic moment is always given by force strength into distance. This is the formula now for magnetic moment for a magnet, which we'll see later. But here, there's a current carrying wire. So whenever there's a current carrying wire which is there in a area, this current carrying wire will have its own north and south pole because it forms a magnetic field. When you have a north and south pole, there will be a dipole moment, magnetic dipole moment there. So there's a magnetic moment because of this as well. So whenever you have a current carrying wire and pass current through it, the magnetic moment formula is always going to be given as NIA. So this NIA is called magnetic moment, capital M. So torque will be equal to mb sine alpha when m is a magnetic moment. How can you find magnetic moment of the coil? Basically, the magnetic moment is this way. Okay. So magnetic moment, use your right hand now. So use your right hand. This is my current. This is my current. This is my magnetic moment now. So current is being this way. So magnetic moment is going to act outwards. So if I give you a question like this, like what is the direction of magnetic moment in this? Use your right hand. Current is your magnetic moment. So magnetic moment for this coil will be acting outwards. That's the information you should know. And okay, so torque NB. So we can give the vector form torque equals to M cross B. So this is going to be the torque experienced by your rectangular coil placed in uniform magnetic field, which is have a current flowing. So this concept of this is used in a machine called moving coil galvanometer. So the next topic in the next video we're going to do is moving coil galvanometer, its applications, and then cyclotron, and of course you have parallel current carrying wires, force acting on it. So let's finish this chapter with this information that a rectangular coil, it may be a circular coil, any coil you go for, if you pass current through it and be kept in magnetic field, there will be torque experienced. And the torque depends on the area, number of turns, magnetic field, area matters. So a rectangular coil is in a circular coil you rotate now. The one with the bigger area will be the one which will be having more torque. If my question is, if I have two coils, one is regular and one is irregular, but same area, what happened to torque? No change in torque. Because area matters and not the shape. So torque depends on the area, depends on the current you pass through, it depends on the magnetic field and the number of turns. And here the angle alpha is the angle between the normal of the coil and your magnetic field, or in simple terms you can say the area vector and magnetic field. So this is my area vector and this is my magnetic field. So this is this and this angle is called your alpha, and theta is the angle with the coil. So when you're given with the coil, 90 minus you do and then use this formula of torque, which is sine alpha. So as usual, before finishing this topic or finishing it off, what we see next week, next topic or the next video is these things. And as usual, I say goodbye. Before saying goodbye, we'll do the summary of the part what we did today.
Magnetic Field Part 2 Summary. A charge moving parallel, anti-parallel to magnetic field will not experience force. In transverse electric and magnetic field, a charge moves unreflected when force due to both are equal and opposite. Magnetic moment of a loop depends on area and current in the loop. Torque is produced when a current carrying coil is placed in uniform magnetic field. Torque experienced by coil depends on area and not the shape of the coil. Magnetic field cannot accelerate charges. Kinetic energy of a charged particle cannot be increased by magnetic field as work done is zero.